morning with the limited time we have. We want to start and get into the second chapter for the course. So the first chapter was on atoms and how they affect behavior of electronic devices. So now we are going to chapter 2, which is on DC circuit theory. My learned you guys did applied electricity. So me sheda near Juma, I don't have any big work to do because you did applied electricity. It looks to me like they've done all the hard work for me already, isn't it? You did this Norton theory and Thevenin's theory. Did you do it?
Yes, sir.
Yes, please.
I hope you still remember.
Yes, please.
Norton theory, nodal analysis. What else?
Thevenin.
Thevenin, Norton, mesh
Kirchhoff's
analysis.
law, mesh,
Yes.
Kirchhoff.
I hope you remember those things.
Yes, sir.
Yes, sir.
So if you've forgotten, go and revise because we will need it in the course. Okay, so last time we met in class, we said that voltage was equal to current times resistance. Then we also said Q was equal to current times time. That means that I is equal to Q over T. Right. Please kindly mute yourselves, otherwise there'll be feedbacks in the call. Unless you're talking. If you have a question or you're answering a question, then you can unmute. But without that, you should have to mute yourselves. Then we said that power is equal to current times voltage, which is the same thing as current squared times R, or V squared over R. Then we also said that so we ended up on this part where I said resistors are grouped according to their power ratings, right? Yes. So when you look at it, you can see that this resistor here, we have a 3-watt resistor right here, and you can see that is the biggest. Then we have 2 watts, we have 1 watt, we have half watts, quarter watt, and we even have 1/6 watt around. Now, yesterday we found out that some of the wattages can even be 2 watts. So in mechanical systems, we have 10-watt resistors there. Right? These ones are called cement resistors because they've used cement to absorb all the heat so that they wouldn't really burn apart. Okay. So today we want to look at, so that was just a recap of what we discussed in the last time. Now today we want to look at some very important concepts. What are they? Now there are 2 types of electricity, and I know you've learned that in applied electricity. The DC current and then the AC current. What is the DC? DC, what's the full meaning of DC? Yes, talk. Yes, somehow.
Direct current.
Direct current. How is that different from alternating current?
Yes, please. The DC current moves in one direction, but for the AC current, it does the opposite.
Okay. Did you learn a bit about AC current in applied electricity?
Yes, sir.
What did you learn? How deep did you go?
Mm,
What do you remember?
for the AC current, it moves in a sinusoidal um, way. So it goes up in a positive way, it comes down in a negative way.
Okay, that's was that all you learned about AC in applied electricity?
No, sir.
Was that all you learned about AC in applied electricity?
No, sir.
Okay. I'm asking this because I need to know how far we would go in the class, because it's very, very important we decide on these things. Right? So, like we've said, there are two types of currents, AC and DC. We are not really going to go into them because of time, because you've done some of these already. Now, the alternating current, like you've all rightly said, it alternates. When we say it alternates, that means that if we have a line here, it goes one way, then it reverses, right? So at one point in time it's positive, at the other point in time it's fully negative. That is the meaning of the word alternating. Its polarity changes, it keeps changing every time. So this is alternating AC. All right, AC current. And then we have DC, direct current. And direct current is such that it doesn't change polarity. So the key term is polarity here. Now, in mechanical engineering, most of the times what you're working with is DC. You don't do a lot of AC in mechanical engineering. We just do only DC, right? What you use AC for is very, very small. So in this basic electronics and also at the electronic level, we hardly really use AC. At the electronic level, it's just DC. So we are going to limit ourselves to DC, but we'll be doing part of AC. We'll just be taking a brief, swipe at AC. For instance, when you want to convert AC to DCs for your machines to work with them, because the machines are working in DC, so you need to have an appreciation of how they are converted from ACs to DC for your machines to be able to work with them. So we will briefly touch on AC in that perspective, and then we will get done. Right. Now, circuit. What is a circuit? A circuit, all our all our devices works with a circuit, one circuit or the other, right? So a circuit is a closed loop with a battery and then wires connected to loads and whatever, right? Can have bulbs here, right? So that is a circuit. Right? So a circuit is a closed loop connected to a battery. Now, you know that already. In electronics, there are some devices we use. Yesterday, you saw some of them. We talked about the resistor, but we briefly touched on it. Today, I want us to really delve deeper, a little bit deeper into what resistors are and then why we need them for electronics and how we use them. What are their behaviors? How do we connect them in electronics? But then before I move on, we should have had our first lab here, lab one, so that maybe in class we would just show you how you use the multimeter, how you use it to measure current, how you use it to measure voltage, and how you use it to measure other parameters. but unfortunately, we don't have our devices here yet. So that's a reminder to us to, make the payment early so that we can get these things on time and get to practicalize them before the semester ends. So without much ado, let's really go into resistance. So when I was learning electronics at first, there was one question that I always asked. And the question was this: if resistors waste electricity, all they do is just to waste electricity or reduce electricity, reduce current. Now, yesterday in class, I showed you that the power it consumes is directly proportional to the resistance that we have, or the current flowing through the resistance. As for current, you can't do anything about it. Current will definitely flow. But then resistor, if we don't really want to waste any electricity, and we don't want to waste heat, we don't want to produce heat that we wouldn't need or use for anything, why do we need resistance in electronic circuits? Because it's just wasting power, like it's reducing how much work we can do. But why do we still deliberately make devices that behave like resistors and use them in electronic circuits? Please, does anyone has an idea about it? Why do we use resistors? Yes, Emmanuel.
So we use them because they manage electrical energy and also they control the flow of current.
Exactly. I like that word control because we've already defined electronics as the study of the control of how current flows. Now that means that in electronics, one of the very fundamental tools, components, devices you will use is a resistor. Now, what the resistor does is that it resists, reduces, slows down the flow of electricity. That's what it does. It just that's the only thing it does. So if you have current moving and it's very, very quick, you can slow it down. You can take this. We have a pipe like I drew in class, and then current is flowing through it. At a high speed here is section A. Let's say this is section 1. Now you need to have a few current or a lower current going through to this next section, because if you don't do that, you're going to have a lot of issues there. That means you need to put a resistor here so that it constricts the flow into the second tube. Right, so that are resistors for us. That makes them very, very, very important, ubiquitous devices that we need in electronics. And so we really need to dedicate some time to them and study them so well. Please, do we understand?
Yes, sir.
Great. Now, resistors, number one, are temperature dependent. Temperature dependent. Resistors are very, very temperature dependent. You learned this in senior high school, right? Didn't you? Have you forgotten? Good. So what was the temperature equation? The temperature dependency equation with resistor. Who remembers? RT, right? Or R1 is equal to, yes. Hey, chew poppers forget. You see, that phenomenon is really disturbing you. Plus alpha T minus T0. Do you remember this formula? Or you forgotten? Great. Do you remember this formula or you forgotten it?
Yes,
Sir,
we
we
remember.
I
You
remember.
remember?
Sure.
Good. Where alpha was equal to what? Yes. What's alpha?
Temperature coefficient.
Nuclear expansivity.
So temperature
Coefficient.
coefficient of what?
Of the resistor.
Of
Resistivity.
resistance into bracket T CR. Please, you understand? Hello?
Yes, sir.
Please, you understand?
Yes, sir.
Yes, sir.
Okay. Okay, great. So I can give you a temperature. I can say that copper. So we can say that copper has a resistivity of, or TCR, an alpha of, so let's say alpha copper is equal to 0.00393. Alpha of silver is equal to 0.00382. Alpha of gold is equal to 0.00340. Alpha of aluminium is equal to 0.00429. You don't need to memorize this. Then alpha of tungsten. Do you know tungsten?
I've
Please,
heard
you
of
know
it before.
tungsten.
Yes, please.
Great, what's tungsten?
Tungsten. Tungsten.
The
Tungsten.
hardest metal on the planet.
Hardest metal. Okay, the metal with the highest melting point, right?
Yes.
In its pure state. Great. It's having the highest melting point. And what's the highest melting point of tungsten? Who remembers? Yes. Tungsten melts at 3,422 degrees Celsius. Very, 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 very high. It takes a lot of heat to melt it. Okay, now when you look at this table here, what do we see? We can see that in the table, what element is having the lowest temperature TCR? Hello. If you look at this list here, the temperature coefficient of resistance that we have talked about. All right. Which of the elements is having the, yes, Collins?
Please, that will be good.
Gold. That means that
Yeah.
gold is more stable. It doesn't react quickly to what? Temperature changes. But that's one of the reasons why it is used in space, in building some satellite circuitry. You know, the reason why I'm telling you all of this, one day, I don't know, some of you may get to work with NASA and be at US, researching the next rockets. Nobody knows tomorrow. Now, when you go there, these are things you really need to know, right? So we can see that gold is the most temperature stable, element on Earth, and it's also very conductive, the third most conductive element. So if you're looking for something that would react very, very little to temperature, then we know that we are going for gold. Is that right? Okay, yes, Collins, your hands is still up. Do you have a question or a contribution? Okay, great. So let's say that we are taking copper, right? And copper's TCR is 0.039. Let's say that at room temperature, the copper we are looking at is having a resistance of 2 ohms, right? So let's say that we want to find the temperature of that resistor at 300 degrees Celsius. What will it be? Yes. Can you try your hands on it? If alpha Cu is equal to 0.0393, can you use some 1 minute to solve it for me? What will be the temperature at 300? Yes. One minute. Yes. So what will be the resistance at 300 degrees Celsius? Who has the answer? Hello. Oh, no one has the answer. Or the Shabris have all slept. Or because you just woke up, you don't even know where your calculators are. Some no, AI critical. Hey, it's a son, everybody. This is a class is here. Yes, I to go area. Come on, some. Now, my better go me so. And the way the go here. That guy who said the afternoon class no open by now, what that crowd? Hey, wait, call him. That guy is asleep. I didn't take note of his name. I should have. What that crowd? Okay. So yeah, what is the resistance? Yes, what will it be? So when we are looking at it, the formula will be R at 25 degrees Celsius times 1 plus alpha changing what T. And so at 25 degrees Celsius, we have 2 ohms and 1 plus 0.00393 times 300 minus 25. And this should give us, what will we get from it? So 300 minus 25 will give us what? 275 times 0.00393 plus 1 will give us 2 ohms times 2.0808. You multiply by 2, and the resistance will increase to 4.1615 ohms. So you see that resistance depends directly on temperature, right? Please, we understand.
Yes.
Hello.
Yeah.
Hello.
I really don't like that you are all sleeping on me this early morning. Rahanda.
Sir.
I think we have to cancel the dawn class and return it back. The unfortunate thing is that the dawn class too, if we bring it back to the day, you won't get very good network. The network is very bad. For me, I'll get good internet because we have this good internet that I can get at the office. But you wouldn't be able to connect and ask me questions. So, Rahanda, so what do I do? Do we cancel the dawn classes? Your people are sleeping on me. I don't like it at all. Okay, then we also said We also said that number 2, so resistance depends on temperature and resistance depends on length, right? We've already established this in class. We said resistivity times length over what? Area, right? Now, when we take these same 5 elements, copper, silver, gold, aluminum, tungsten, they have various resistivities, right? And I think it's good you know them. If you say, why are you on the line? If you say why is asleep, hey, she joined and slept. Oh, great. Good. Okay. Please grab your calculator. You'll be doing some maths for me very soon. So resistivity of copper is 1.68 times 10 to the power -8. Resistivity of silver, Ag, is equal to 1.59 times 10 to the power -8. Resistivity of gold, aurum, is equal to 2.44 times 10 to the power -8. Resistivity of aluminium is equal to 2.84 times 10 to the power -8. Then resistivity of tungsten is equal to 5.60 times 10 to the power -8. Now, of all these 5 metals, which one would you really like to use? Which one is more resistive? And which one is least resistive? Yes. Who is saving the class? If you look at the resistivity thing we've written here, which one of these elements is more resistive? And which one is having the least resistance? Yes, Elvis.
So when we look at the resistivity, we can see that I can't really see clear. I just joined, but I can see that the one that is 1.68 at the top is more resistive than the one at the down. At the least, the last one.
Okay, thank you for your comment. Thank you for talking. I'm glad you talk. Okay, when we look at it carefully, we can see that copper is having 1.68 times 10 to the power -8, but silver, you can see silver is having the least, right? 1.59. Then tungsten is having the highest of all these 5 elements. Now, these two things are very, very important. Temperature and length, very, very important. How do you mechanical engineers apply this in your working life? Let's look at these 2 questions. There are 2 questions here. Let's look at them and attempt to solve them. All right, question number 1. I think I should increase the font size of question number 1. Okay. So that okay. Great. So this is question number 1. Let's see how you guys really use this in your work as mechanical engineers. Please, can you see my screen?
Yes, sir.
Yes.
So kindly take notes of it. Can somebody read for us? Okay, Rahanda, great. Rahanda, let's go. I want a girl with a nice voice, not a boy. The guys who play bass in my ear, I don't like that. Rahanda, let's go. Yes.
A maintenance engineer notices that a 12 voltage, 55 watts,
Yeah, let's go.
55 watts tungsten halogen headlamp in an automated inspection machine draws a very large current immediately after setup, but the current decreases after a few seconds even though the supply voltage remains constant. A. Calculate the operating resistance of the lamp filament. B. Explain why the current decreases after startup. C. Relate this behavior to the temperature coefficient of resistor of tungsten.
Great. Thank you very much, Rahanda. Yes, someone's hands is up. Okay. Please, you understand the question? So in our headlamps, right? Most of headlamps. I told you what headlamps was. Headlamp is the car's light, right? All the headlights of cars. We call them headlamps. Now, most of the times, there are various types of headlamps. We have LED headlamps. These are more modern. But the olden cars, the ones that glow and uses heat. So it's very hot. When somebody turns on their headlamp and they turn it off, you go to it, closer to it, and it's very, very hot. We use tungsten, right? Tungsten element for it. Why do you think we use tungsten? We use tungsten because much later, I think maybe level 300, you're going to learn heat transfer. And heat transfer, you would learn that any hot object, right, emits radiation. Any hot object emits light, radiation, right? So all hot objects in this world emit radiation. And the power of radiation is directly proportional to the temperature of the body. All right. That's heat transfer. You will learn it in black body radiation. Now, what that means is that the hotter the object, the more brighter it appears. Now, somebody will be asking me, you see, yesterday we established in class, was it yesterday, Monday? We established in class that even ice water is hot because if you convert it to Kelvin, it is 273 degrees Kelvin. So you may be asking, that means ice water is hot. If ice water is hot, it doesn't emit radiation. It really does emit radiation, even ice water, right? But the radiation it emits is called ultraviolet or infrared. So we have, infrared radiations. Right now, as the temperature increases, the waveform becomes visible, more visible with temperature increase. Please, you understand? So if temperature increases, then it becomes more visible. That is how come you don't see the radiations coming from, ice block. But then that's also how come we can use a camera. We have thermal imaging camera, right? So we have thermal imaging cameras, and thermal imaging cameras can take the temperature profile of any hot object because our eyes are sensitive to light, visible light. But those cameras are not sensitive to only visible light. Those cameras are sensitive to radiation, invisible light, and all of that. So it can see them, and then it can depict a picture of how that temperature looks like, right? So we want headlamps. We want something that is so bright on the road that can see very far. That means in those days, before we discovered light emitting diodes, if we wanted to get light, that means we really need to get light that was bright at very, very high temperatures. And that was how come we got to use tungsten, right? We got to use tungsten because tungsten could endure a lot of temperatures because we knew that we needed high temperatures to be able to get significantly brighter light on the roads, right? And so tungsten became the obvious choice, right? Now, typically in the filaments of cars their temperatures are around 3,000 2,500 to 3,000 watts, right? 2,500 to 3,000 watts, 2,500 to 3,000 degrees Celsius, right? So if you take something like copper is around 1,000 degrees Celsius. It will melt. If you take something like gold, it will melt. It's around 1,000 degrees Celsius. They will all melt. Right? That is why the sun, which is the hottest object in our solar system, emits radiations and emits visible light all around us. Right? It emits dangerous radiations that we don't even want to receive, but we still get them. Right? So when I give you this question, or when we have a tungsten filament, now remember that we said at cold temperatures resistors are lower. At hot temperatures resistance increases. So if they tell us that 55 watts tungsten, right, that means that, so we can start with the solution. And just like how you did in senior high school, in fact, that is always how I prefer my solutions to be presented to me. Just like how you did in senior high school. You will start and say, given that power is equal to 55 watts, and then voltage is equal to 12 volts, right? We know that power is equal to V squared over what? R. This means that R is equal to V squared over P. Then we can find R to be equal to 12 squared over 55. What would that be? Yes, Afia Sewa. Mami Sewa.
2.618.
We have
2.618 ohms.
2.618 ohms. Thank you very much. So when we go back to the question is asking us, calculate the operating resistance of the lamp filament, right? So when it is drawing 55 watts at 3,000, because that's where it's operating. That's where it's operating, right? So it is at 2.6 ohms resistance. Now, the question is telling us that explain why current decreases after startup. So see something here. This is the operating current at 3,000. At 3,000. The question didn't actually give us a temperature, but at 3,000. So B. At startup, what happens? At startup, temperature is low, typically at room temperature. Assume you've parked your car, right? So you've parked your car throughout the cold in the night. Temperatures is low, right? So T is usually at 25 degrees Celsius. And at 25 degrees Celsius, we can assume that the resistance at room temperature there for tungsten filament is 0.3 degrees Celsius, right? In our use case, let's take 0.3 degrees Celsius. Please, do we understand?
Yes,
Now, at
sir.
0.3, come again. Did you say yes or no?
Please,
Please, I
sir, please
said
go back.
He said I should go over it again.
Yes, sir.
Okay. Which part? Is it this part, the power part?
Yes, sir. Yes, sir.
Okay. So you understand this part, right?
Yes, sir. Yes, sir. The second part.
And you understand all of this.
Yes, sir. The second part.
So part B.
Yes, sir.
All right, so we are now starting. Let's pay attention closely. Now we said that temperatures vary and resistance vary with temperature. That means at cold temperatures, resistances are what? Very low. Is that right? At cold temperatures, resistance are very low. So at 3,000 watts, the resistance is 2.618. At 25 degrees Celsius, the resistance will be very, very low. Very, very low. Okay, and usually it's around 0.2, 0.3 degrees Celsius. There are calculations we use to estimate what is the resistance at room temperature, but just for the case of the course, let's take it to be 0.3 degrees. Sorry, 0.3 ohms, not degrees Celsius. Sorry. I think that may be where you guys are getting the confusion from. So 0.3 ohms. Okay, now if our lamp is at 0.3 ohms at start, when you plug it into voltage, right? If the lamp is at 0.3 ohms, what will be the current that will flow through it? It will be V over R, right? And so we have 12 over 0.3 ohms. And what do we get? 40 amperes. Very, very huge current. So because it is cold, right? Because it is cold, it is going to take, the resistance is very low, 0.3 ohms. And so it's going to draw a lot of current. Now, what happens is that this current draw, instantaneous initial current draw, is so huge. So it's going to heat up the resistance, right? It's going to heat up the tungsten filament element very quickly in a very short period of time. That is why when you are turning it on, you can observe that it doesn't start brighten all of a sudden. It looks like it's a glowy, it start brightening small, glowing, then it comes on, right? So all that time that is glowing, it is taking that 40 amperes all that time, right? So it starts from a very high 40 amperes, then it takes it until it settles at that 2.618 ohms. Now, at that settled temperature of 2.61 ohms, at operating point temperature, what will be the current at 3000 degrees Celsius? It's still going to be V over R, and V is what? 12 volts. R was found to be 2.618. Well, what's the current we have here?
4.583.
4.583
ampere.
amperes. Great. So the current draw will start at an instantaneous high over here of 40. Then it would settle down to a stable high of 4.6. And this period happens in a very short time compared to all of this. Please, do we understand?
Yes, sir.
Yes, sir.
Great.
Jose,
Please, which part don't you understand?
so I think calculating the resistance for the 30 degrees Celsius.
The 3000 degrees Celsius.
Yes, sir, the 3000.
Yes. So in calculating the resistance for the 3000, we said that the halogen bulb operates at 55 watts, right? And then 12 volts electricity, right? So that means that, and then there was a fault. And one guy was trying to inspect the fault and see what is happening, what causes it. Then to his shock, and you would really see a lot of these conditions. At start, there is a very large current that immediately flows at startup. But the current decreases after a few seconds, even though the supply voltage is constant. So we are trying to explain why that happens. And this is something you are going to see in your life. In fact, all through your life as mechanical engineers, you are really going to see it. It happens in industrial machines. It happens with motors. When motors are starting, it's the same thing. They drop very large current, right? Now that condition here that we've established, that we've observed that they always happen, where devices will drop very large current at start, then will settle down, is called inrush current, right? Inrush current or surge current, right? So it happens because of the nature of these materials we are using. Please, do we understand? Do you now understand?
Yes, sir, I get it now.
Yes, sir.
Good.
I see.
So as
Yes, sir.
temperature rises, the atoms vibrate more, right? And because they vibrate, you see, I spoke about this yesterday, that when temperature rises, atoms are having more energy to vibrate, right? And so they are vibrating more. Because they're vibrating more, electrons are scattering more everywhere. And so there are a lot of resistances that you are going to face if you are an electron and you're moving through this crowd, right? So the resistance of any material is directly dependent on temperature. Is that right? Now, the last part of the question C, was that explain this behavior, relate this behavior to the temperature coefficient of resistance, right? So how will we do it? We know that the temperature coefficient of resistance for tungsten filament is 0.045, right? Change per degree Celsius. So to explain it, we will just use the equation, right? Using R is equal to RO times 1 plus alpha T minus TO, right? We use this. Then we will use it to explain. Now, when you observe, you can say that higher resistances would lead to low current, right? Higher resistances would lead to low current. You see that in this case here, when resistance increased, it resulted into low current. Then at initial startup, when resistance decreased, it resulted in high current, right? So higher resistances would result to low current. That means that, and then low resistances will result in increasing current. So there is some kind of an automatic, control here. We call that behavior self-limiting electrical behavior, self-limiting. And you see it, in many places in mechanical engineering. Right. Now, the lamp behaves like in a certain loop. So when you look at it, you can see that the lamp behaves this way. We first of all have electrical current, electrical input. Then that electrical input would affect, so the electrical input that we gave it in at startup, right, determined how much current, right, how much heat, so thermal response. So the electrical input was what raised the temperature of the tungsten filament bulb. Then when the temperature raised, it began to automatically regulate how much current is flowing by setting the resistor. So it's automatic. The system is just regulating itself. So resistance and then current into brackets current. Right. So this is some kind of a control system that we have given it a name, thermoelectrical control loop. So if you select your materials correct, right, the system should not fail. The system should be able to work for a very reliable, period of time. Please, do we understand?
Yes, sir.
Great. Now, before we close today's class, let's solve the next question. So there are two questions here. Let's solve the next question. Right. Let me grab this to a different board, different place where we can have enough space to solve. Okay. So we have Okay. I'll be sharing this board with you so that we can go over again later. All right. So, please, do you see the screen? Do you see my screen?
No, sir. Yes, sir.
Okay. Okay, great. So because of time, let me read it so that we can solve it quickly. A mechanical engineer is designing a compact drying chamber powered by a 12-volt battery using tungsten filament heating. The target air temperature is 350 degrees Celsius. So that is where we want to heat the drying chamber to. Given that the supply voltage is 12 volts, and this really happens. We use this in cabinet dryers. You will learn more about that later on. Right. Now, the filament power is 60 watt, and tungsten's TCR, temperature coefficient of resistance, is 0.0048 degrees Celsius per degree Celsius. Number one, determine the operating resistance. B, what's the operating current? C, explain qualitatively how the filament resistance changes during warm-up. Then explain whether tungsten is an appropriate material choice or not. You see, that's a very interesting question. Isn't it very interesting? Don't you like the question?
Sir, we do.
How can you not like it? Opamen like it. Good. So you'll be designing all of these things in your life as mechanical engineers. In fact, that's what you do when you go to the industry. There was a time we visited one industry in Takrade, and they were into drying, and these were some of the things they were doing there. So you need to be able to design your dryer, the size of the dryer, the surface area of the dryer, and how much electricity you would be using. Right? So you need to understand these concepts so that you can design those systems. Now, so we were given, so like I said, we're given 60 watts, right? The power is 60 watts. Then the voltage is 12 volts. Then we are given alpha of tungsten to be 0.0048 per degree Celsius. Okay. Now, question A. Question A is asking us to find. Question A is asking us to find the operating resistance. Right. Operating resistance. What will be the operating resistance? Yes.
2.4.
2.4 ohms.
It will be what?
2.4.
2.4.
You've already calculated it.
Yes.
But what formula did you use?
Sir, we use that.
I used V squared over P.
Over P. That's excellent. Then when you do that, you're going to get 2.4 ohms. Then
Yes, sir.
the next question was operating current. What will be operating current?
5 ampere.
5 amperes.
Great. Operating current. How did you get it?
V is equal to I
V
times R.
over
So I is V over R.
P.
So 12 over what?
2.4.
12
Over 2.
2.4.
And that gives you what?
Sir, me, I use over V.
5
I
amperes.
give
says 12 over 5.
You got what? Yes. Now I'm confused. So what did you get for I? 12 over 2.4 gives you what?
5
5
I is
ampere.
amperes.
60 over 12.
5 amperes. So 60 over 12 should also give you 5.
Yeah.
Yes. So that's also correct. 60 over 12 should give you 5.
Yes.
Melky is really having a very bad network this morning. I don't know where she's living at. Okay, so that's that for us. You guys are very. Now what's C? Explain qualitatively how filament resistance changes during warm-up. How does it change during warm-up? See, you see how my questions are going to be. You have to apply your master two poor pass na the foul. Could di baba some yes, Elvis.
Okay, so the at the beginning
Yes.
the tungsten filament is around paper. So
Please
when
speak closer to your mic. I'm not hearing you clearly.
okay, so you can hear me now.
Yeah, I can now hear you.
Okay, so at the beginning the tungsten filament is at room temperature, and then
Yes.
when the inrush current is coming, the resistance of it is relatively lower. You see, because it
Yes.
is cold.
It's
So it
cold,
is cold
yes.
at that moment. So
Yes.
now it experiences a warm up process where the electric current is converted into heat.
Yes.
And then as the temperature increases, of course, there will be vibrations between the atoms of the tungsten.
Yes.
So this would impede the flow of the conducting electrons.
Exactly. Yeah.
So I think, and then the since the inrush current came at first, it will now,
Yeah.
the warm-up phase, it will now speed up until the
Exactly.
resistance continuously during the warm-up phase until
Increase.
it
Yeah.
reaches 2.2 ohms.
Yes. Exactly. So
Yes,
so
yeah.
that is why at times when you are in the industry, you turn on high consuming devices, then you be seeing some sparks because 40 amperes is very big, very, very big, and it can produce these sparks. And that is why we always say that if light goes off at your houses, turn off all the loads that were on. Because if you don't turn them off, then all of them are all turning on at the same time. These inrush currents are coming in. This is just a lamp and it's just 40 amperes. So assuming you have ACs, you have all of those ACs that are on, right? The surge goes into hundreds and all of them are drawing it suddenly through your house's DB. So the system will just go down if you're not lucky, right? So we always recommend that when there is light off, turn off all your ACs so that when it comes on, the surges will not happen together to break down the system. But that is why in the industrial settings, and this is just one headlamp. So imagine you have an industrial motor. It's huge, very huge. So, but we have solutions for it. We call something soft starters in the industry that we use to limit how much inrush current flows into motors when they are started, right? But you can't always prevent it. Please, we understand. Yeah, so that's why in the industries we have something we call variable frequency drives, VFDs. What they do is that you know that the inrush current depends on the amount of voltage. If the voltage is very high, the current will be very high. So what they do is that they reduce the current, they reduce the voltage, they step down the voltage to very, very low volts, around 1 volt. So around that time, the resistor is low, it draws low current, then it hits small, then they increase the voltage. So gradually, over about 5 seconds, so that it doesn't draw it instantaneously. Because in the industrial setting, if you are dealing with industrial motors and it's drawing suddenly, you can burn the whole system down. Yeah, so it's very, very critical. We take a look of that when we are designing our systems. Please, we understand.
Yes, sir.
Yes, sir.
Great. Yes, Collins.
Yeah, sir, please, I want to know whether the vibrating particles that will lead to the increase in resistance when the surge current passes through the components.
So when the surge current passes through the components, the increase in current means that there is more electrons flowing. So when there is more electrons flowing, there is more collision, there is more vibration, right? And so
So
there is
the
more.
collision, meaning the collision leads to the increase in resistance.
So the collision is what leads to the increase in resistance, right?
Oh,
And the,
okay.
yeah.
Okay.
So the collision
Thank you.
raises the temperature. Then the temperature would make these electrons more excited, right? So they'll be vibrating. There'll be an increased vibration. So naturally, its resistance would be raised even after that huge volumetric flow of electron have come and passed. Please, you understand how it works?
Yes, please.
Good, good. So then it stays hot, and as long as current is flowing through it, it is that hot. In fact, this is also why we advise that in the house, when you're ironing your clothes, iron them in batch and don't iron them in pieces. Because if you iron them in batch, when you start turning on, when you plug your iron, because it's cold, it draws very huge current to heat it to that temperature, then it starts drawing small. So it applies everywhere in your engines, your car engines, right? If you start the vehicle, it will draw more fuel to heat the vehicle's engine to the ideal temperature it needs to work, right? Then it starts drawing, incremental fuel to sustain that temperature for you to be able to, produce or do meaningful work. So it happens everywhere. Surge happens everywhere, right? We call that time delay, and we'll look at it into details later on in application to your mechanical engineering course. So it really happens everywhere. Please, do we understand? So let's answer the last two questions. Then we can call. I know it's 6 o'clock, but please give me some few minutes additional so that we'll finish this. I don't want us to come back to it. So when we look at it now, at the operating temperature, which is 300 degrees. Sorry. But please, someone is introducing noise. Kindly mute your. Okay. So at T1, hey, now no person now jamming sound. Okay, T1 is 350, right? The question gave us 350 that it hits to 350, right? And we found the resistance at T1. So the resistance is at T1, which we've calculated to be 2.4 ohms. Now, the question also gave us that TCR of tungsten was equal to 0.0048 per degree Celsius, right? And we know that R cold, let me do R0, is equal to R1 or R hot times 1 plus change in temperature times alpha. Is that right? Okay. So we just plug them in. We know R1, which is the final temperature. Sorry, this is R0. Sorry, that's R0, and here is R1. I've mixed them up. You see, they're just copying, so they couldn't catch me that when I did it wrong.
Yeah, I was about to say
We thought you were bringing another formula.
Thank you very much. I just wanted to see if you were all hearing me or you are asleep. Some of you are still sleeping. So I had to
Sorry, I'm
provoke
not
you.
asleep.
Okay. So yes. So we've so we know R1 is R hot. Let me just use R hot. Then this will be R cold, RC. Then we have 1 plus alpha times T. So we can plug them in. We know R hot. R hot is 2.4, and RC is so 1 plus 0.048 times 350 minus 25. And so when you evaluate all of that, what will it be? All that number parts. So what will it be? Mami Sewa.
I believe the 350 is 0.25.
Come again. It's 350 minus
The 350.
25. 350 minus 25.
Okay.
350 minus 25.
So I had minus 41.
No, so I mean 1 plus 0.048 times 350 minus 25.
0.0048.
The 2.56. 2.56.
0.56.
Yeah.
Great. So that means that RC will be equal to 2.4 over 2.56. And that's what, yes.
And that's
Do we?
0.937.
Great. 0.933.
Yeah.
Please, we understand.
Yeah.
So
Yes, sir.
so we can see that. So that would be 0.94. Now that means that a startup, the inrush current will be equal to 12 volts over 0.94. And what do we have?
So, the 12.76.
Which is like 12.8, right?
Yeah.
Yeah, 12.8 amperes. Great. Please, we understand. So you see that initially at startup, it draws 12.8. Then when it settles down, it draws 5 amperes. Right? That's a very huge difference, more than twice. Right? And that's how electronic systems behave. So when you are sizing or selecting a wire, like I was saying in class yesterday, somebody will get a headlamp that has spoiled. Then you need to replace it. Then, maybe the wire doesn't really fit into it, and you want to find another wire, and you're like, oh, nase headlamp there. Oh, nase headlamp there. Masa, ube should be car. This is somebody's car. You need to be very, very careful the wire you select. Let's do the wire selection for these questions. Then we will call it a morning. Right now, in vehicles, and in automotive engineering, we recommend that your current density, if you say current density, you know what current density is, right? And I'm a referee. Physics, current density is equal to what?
Say review.
Come again.
So we don't remember.
Okay. No, that one was abstract physics. It was one of those confusing parts of physics we didn't remember. Current over area, right? It's called the current density, J. Now, for automotive, what we recommend is that in automotive engineering, all your current densities should be between 4 and 8 amperes per millimeters squared. Now, there are two currents here. So which of the current do we use? Do we use the inrush current or the continuous current? So you see the inrush current is 12.8. Then the continuous current is 5. Which one do we use in selecting a wire size? And why?
The continuous current.
We use the continuous current. That is very excellent. Why? Why do you suggest that we use a continuous current? Yes, so
I don't know how to
continuous.
explain it, but that's how it has to be.
You see, Ladies are very, very intuitive. Yes, Elvis.
So I think that the reason why we are using the continuous current is because during the warm-up process, that is the one that is being used. You see that the inrush current was what was generated, like that was what came into the system at first, but that's not what
Yes,
is moving through.
exactly. That's very brilliant. I like that. I like that someone is clapping for you, but you deserve more claps. So that is just it. The reason why we don't use inrush is that inrush lasts exactly. You see your people are clapping. A lot of them are clapping for you. You should feel the clapping. Good. So we don't use inrush current because inrush current happens over milliseconds. And when it happens, it doesn't happen again unless you are turning it off and temperature is coming down. As long as temperature is operating, it doesn't happen. As long as the device is operating, it doesn't happen. Right. So that's also one of the reasons why when you go to the industries, they don't usually stop their devices or their large industrial machines. They don't stop them. When you go to the power sector, those of you that work in the power generating sectors, in thermal sectors, they don't stop these large systems unless there is a mandatory maintenance. In fact, at times in the power producing sectors, we call something um, what's the term I'm getting? I'm forgetting right now. I can remember it in the course of it. So we start a generator, we synchronize it to the grid, and it's not producing huge power, but it's just running, right? Cool. We call it spinning reserve, spinning reserve, spinning reserve. So we have spinning reserves and reserve margin. These are two different things. So we just start a generator, we synchronize it to the grid, and we allow it to run. It's just running. Because if you stop a generator and you want to start it, it will draw huge fuel, it will draw huge electricity, like huge energy, right, from the start to stabilize before it starts giving you good job. Right. So those huge ones at the start, we don't really need it because it's just momentary. It's just some few microseconds and it can cause a lot of harm. Right. So we don't use that one to actually size, but we rather use the continuous current. So I'm saying that, to mobile engineering, what we actually recommend is that your current density should be between this. That means you can choose any value, right? You can choose to say 5, current density. Let's say J is equal to 5 amperes per meter squared. That means that I will be equal to J over A. Will it be that? Let me see. Sorry. J is equal to I over A. That means A will be equal to I over what? J. So if our I is, what was the I? The I that we had was 5, right? Was it 5? 5 amperes. Good.
Yeah,
So I was 5
yeah.
amperes. Great. So if I is 5 amperes, and then we are selecting a current density of 5 amperes, let's do 4. Let's do 4. So 4 amperes per meter squared. Right. What it means is that we are going to have 5 over 4. I feel what will we get?
1.25.
1.25.
Yeah.
1.25 mm squared. So that means that the wire size that should be used for this heater should be a 1.25 mm squared. Oh, sorry. So this is not even an automobile application. Sorry. So this is even this one is for the first question. So for automobile applications, we recommend that one. But for these high heating applications, we recommend two to three. So the wire size will be big, right? It will be a little bit bigger because it's in an ambient temperature where there is also ambient heat coming to affect the system. Please, do you understand?
Yes, sir.
Great.
Yes, sir.
So, yes. Is anyone having any question before we close the class for this morning? Now you can see this table here. In fact, I've sent the recommended learning materials to your classroom, and you can just go through it. And I'll share this board to with you, this whiteboard to with you, so you can have it for your revision. Now, when you look at it, these are the prefixes we use for resistors and for capacitors, and it's good you need to know it. I know you know it already, but it's good you revise and then have it in mind. Right. Okay. Any question? Okay. So yes, Elvis.
Okay, so relating the current density to resistivity. Okay, and
Yes.
I wanted to say that I wanted to ask that you see that in both equations I can see area. So,
Yes.
so can I in a particular question where I'm trying to find the resistivity and then uh, can I fit, let's say, the area of the the current density into the resistivity and then try to do some calculations.
Oh, why not? Why not? So it depends on what you are looking for. So let's say,
Yeah.
yeah, great. I feel you want to weigh in, please weigh in on it before.
So,
Girl never matiko, if you have a matiko, small. Okay. So we have R is equal to rho L over. So if we say J is equal to I, then you make A the subject here. So we have I over J. Then you substitute it back into R. We are going to have rho L over I over J, which is going to be equivalent to Ri over J is equal to rho L. Or we can say R is equal to J rho L over I. So we can have this equation and it's valid. Now what it means is that it is the, so what this means is that what will be the resistor that we have to select at what accepted current density and current with its resistivity and then length that will suit, that will meet the current density and then current. So yes, it's a useful equation you can keep, but that's when you're actually designing circuits. And for those of you that will be going into robotics, you would really be doing most of these calculations. But those of you that will be going to large mechanical systems, look, you can forget about it and live your life, enjoy your life. But those that want to go into robotics, and look, this is very important. You can spend your time and then go deeper on this. Is that right?
Okay, sure. Thank you, sir.
Great. All right, so guys, thank you very much. Those that were dozing on the call, thank you all for joining. You see, today there you can take yourself and eat because I didn't ask you to turn on your cameras. I didn't see, but and I know we would meet more. I wish we could really maintain this class so that we would really have a very good internet connectivity. Have a very nice day. Have a very productive day.
You deserve.
Yeah. All right. Bye bye.
Same to you, sir.
Genevieve wants to say something.
So, no,
Yeah.
say bye bye.
Genevieve
Okay.
said au revoir.
Okay. Genevieve.
Sir,
Wow.
reply in French.
Masamire free my
Eh,
friend Joe.
Rahanda, go and sleep. Go and sleep. Now, I'm sad. So, what you put up your German in Sasso?
Sir, Genevieve, question.
Okay,
Hey,
Genevieve, you have a question. Scandy,
Yes, Sir
Godfrey.
Genevieve
she's
wants to
lying. So,
ask
she's
a
lying.
question.
So, we have closed. So, I thought you were gone.
Godfred, your hands is up. Do you have a question? Okay, Bright.
Said they thought you were gone, so they were raising their hands to see.
Okay, yeah.